So in the previous classes we have discussed about the divergence and divergence, what is divergence like and its mathematical representations. Now one very important theorem related to divergence is Gauss Divergence Theorem, which we are going to discuss in this class. So this class Gauss Divergence Theorem, also sometimes called as Gauss-Ostrogradski Theorem, based on the theorem that has been proposed by the person. So we were going to discuss this Gauss Divergence Theorem, and possibly we will also prove how this theorem stands valid. So first let us see what the theorem states. This theorem states divergence divergence of a vector field, any vector field it may be, over a volume, any volume, is equal to the surface integral we have already discussed in our previous classes. So equal to the surface integral of the normal component of the vector, that is the vector field, through the closed surface boundary of the, or rather we will say through the surface boundary bounding the volume. So that means the divergence of a vector field over a volume, suppose you are having a volume, so divergence through that volume or of that volume where there is some vector field will be equal to the surface integral of the normal component from that volume, the component which will be normal. So we will simply integrate those normal components in terms of surface integral, and that will be through the normal component of the vector through the closed surface bounding the closed surface boundary bounding that volume. Okay, so now we will, it can be also expressed in the terms, let us write the expression to make it more user friendly. That is del dot a vector, any vector f is there, dv, that will be equals to, so this is, you can see this is the volume integral. We are going to find out the divergence of the volume integral of a vector f. So in a particular volume, since volume v is given here, so this will be, according to the theorem, this will be equal to the closed surface integral of that particular vector f, or ds, or rather we can also write in terms of unit vector f an unit vector ds. So this is actually the expression for Gauss divergence theorem. Once more let me tell you that this theorem tells that if there is some volume, suppose there is some volume is there, of course it is a 3D volume. Now some vector field is there, I mean some vector is passing through it, say suppose. So this vector having f, so we will find the divergence of a vector field over this particular volume v. This will be equal to the normal component, or there will be some certain normal component from this volume. So this will be equal to, through this is, if this is the considered as a surface S, so this will be equal to the integration of all normal components from that volume or emanating from that volume through the surface of this total volume. Okay, so now after this we are going to mathematically prove that this concept is, whether it is correct or not. Okay, but here we will going to consider the proof of this Gauss divergence theorem which I just discussed. So let us see here, in the Cartesian coordinate system we have defined a volume, or like a parallelo, I mean this is a 3D volume of a rectangular parallelopipe. So here we are considering this as structure, I mean this volumetric, in this direction it is dy, here it is dx, and here it is dy as per the direction of the coordinate systems. Now to prove this Gauss divergence theorem, so we can say by definitions, so we'll simply write by definition of divergence. We remember the definition of divergence, so we can simply write del dot f that we have previously learned in our previous classes, that is del x fx plus del of fy del y plus of del fz del z. So this is the definition. From the definition of divergence we have previously got this expression. So therefore from here we can write that del dot f, which is actually we are going to find out as per the Gauss divergence theorem. So that is dV. Of course this will be volume as per the Gauss divergence theorem. So simply this will be equals to the volume integral of the whole thing, that is del fx del x plus del fy del y plus del fz del z, and in the direction of dx dy dz. Okay, so this will be the expression. So let us mark this expression as our expression 1. So from now consider the elemental volume. As in figure you can see that we have considered this volume as an elemental volume. So there will be three different direction, in three different direction, in x direction, in y direction and z direction. So three directions are there. So we'll analyze the three direction one by one. So let us consider the elemental direction or the elemental volume in case of x direction first. So for considering, we will write this considering elemental volume V, as in figure you can write this only in the direction of x we will write. So this V del of fx del x dx dy dz, and that will be equals to surface integral as per the theorem. This will be equals to the surface integral of del or dfx, not d, it is del x dx and dy dz. So this, in this x is already taken inside because this is represented only x part. I mean we are considering only in the x direction, so we have taken this only del fx del x here, and we have only taken this x term here, and so it will be, so we have correspondingly taken this dx term here and we have left out this dy and dz. So similarly in other direction, so from here also we can write here from x1 to x2 del fx by del x dx equal to del fx2 minus fx1. That is what we here written, that in direction, suppose this in x direction, the increment or of the volume, or rather I will say from x1 to x2, suppose this point is your x1, is this x direction, x1 and x2. So from x1 to x2, the differential of the vector, that is fx, in only in x direction, let us suppose take by the difference of this function, that if from x, simply by definite integral we have used, and we have calculated it as fx2 minus fx1. So similarly we will consider, or we will write the other few expressions for the other. Before that, this, let us write this fx1, and what are the fx1? These are considered as fx1 and fx2 are x component. You have to remember this one, x component of the vector on the back and front side, isn't it? Because this x direction, what is, if this is your x direction here, this is your x axis, so one side will be, this is your front side, another will be your back side. So two surfaces are there. So we have made the difference of the two vectors emanating from surface, this surface and this surface, as a difference of this fx2 minus fx1, right? Therefore we can write this v of del fx dx del x dx dy dz, that will be equals to surface integral of, simply we put this fx2 minus fx1, fx2 minus fx1 dy dz, that is equals to, we can simply write f of x b sx. This is your equation 3. Okay, so just we have put that this dy dz is your x, since the y and x, y and z, this y and z makes up a surface, that is this particular surface. So we have represented at surface. This A stands for the surface presented by the axis y and z. So now similarly we will find out the component vectors, or rather we will find out the volume integral in the direction of y and z. Like here we have found out only the component vector in x, so we can now find out similar process the component vectors or the volume integral in the direction of y and z. So let us see what will happen. So similarly we will find, simply we like, similarly we can write the volume integral of del fy del y, x we have already found out, so we can already write dx dy dz, this equals to fy b of sy, right? So this is one equation we have got. Suppose this is equation 4. Next, similarly, now we have found out in terms of y, we can find it out in terms of z also. dfz del z dx dy dz, that will be equals to surface integral of fz d of fz. So this is your equation 5. So we have found out in all the directions. So simply we will integrate, we will join all the three component vectors, and finally we arrive at this expression del dot f, that is divergence of a vector f, that will be dv, that will be equals to surface integral of f into ds. Why? This f is now considered as the addition of the component that we obtained previously in x direction plus y direction plus z direction. So we have covered all the three directions. We are simply writing that this is equals to the surface integral or the overall surface integral in all x, y, z direction, and we have correspondingly we got this result. So we can found, and this is your Gauss divergence theorem which is being proved, right?